Welcome back to our lesson of physics. Where we ended, we were looking at internal resistance, work done in pushing electrons from one terminal of the battery to the next terminal. That as electrons are being pushed from one terminal to another to flow through the external circuit, work is also being done. So that work done is to overcome the opposition to flow of electrons from that terminal, from the positive, say, to the negative, and vice versa. Now, that opposition is what we call internal resistance. And sometimes, when you switch on any electrical appliance, or when you switch on a circuit with no load, a load is something that takes up electricity. So when there is no load, but you switch on, you will notice that there will still be a drop in the reading of the voltmeter. Now that drop is as a result of the opposition to the flow of current in the battery itself. So that is what we call internal resistance. So our next illustration in digital science is to have a small experiment to see how the internal resistance, the opposition. When I say internal resistance, simply understand that it is opposition to flow of current from one terminal to another within the battery. Are we together there? Yes. Now, let us look at this in the next illustration. You see, in this circuit, we have a battery, we have voltmeter and ammeter. So, as the opposition to the flow of current reduces, as shown by the change there in the rheostat, look at the ammeter, look at the milliammeter. What is happening? The milliammeter pointer is increasing, meaning the current flowing actually increases, because the less opposition you get, the more easy it is for you to do work. Is that okay? So the current increases because the resistance has decreased. So the table shows, let us look at the table. Let's get to the table now. As the table will be filled, let us look at it as it is being filled. The milliammeter keeps on. Reads the current. You see 68 there, milliamps, then 83 milliamps, and then we get the next one. So as the current increases, the voltage, what we call the terminal PD, also decreases. So take a look at that. That's a very important experiment, which actually is also available in virtual lab. It is one of those important experiments you do in exams. Ohm's law is also, you can use this. Using Ohm's law, you can determine internal resistance. So once that is done, look at the graph. A graph is drawn. So you have a graph of current against PD. That PD is E minus V now. Okay? E minus V meaning the difference between the EMF and the voltage across the load as the load is either increasing or decreasing. Do we see the graph? Yes. Now the slope. The slope is y over x, change in y over change in x. Change in y is change in current. The x is change in voltage. So the change in voltage, we look at that. It is 1 over the slope. So our resistance is 1 over the slope. 1 over the slope. Why? Later on, I'm sure when we're going to learn about Ohm's law, which talks about potential difference is equal to current times resistance. Current times resistance. So when you divide voltage by current, you get resistance. Now when you change, you take the other one up. Here we have taken current up. That means you're getting, what do we call that in mathematics? Reciprocal. 1 over S. 1 over S. So 1 over S. So that is how we get our internal resistance. So I hope we have understood now. Internal resistance, the resistance to the flow of electrons from one terminal to another is what we call internal resistance, and we can get it by simply taking readings on the ammeter and voltmeter as the load is reduced to see how internal resistance can be obtained. Now, application. We are going to look at the next slide. In our next slide, we are seeing, now, in a house you need to know because of these loads and the resistances and so on, you need to know how batteries are connected. And when you know how batteries are connected, it helps you to connect the loads in your house. You have a TV, you have a fridge, you have a flat iron. You should be able to understand what their load rates are. How many volts does a flat iron take? How many volts does a fridge take? What about the current? That is sufficient so that it does not blow. So this is linked to the connection. So in this animation, which is also in digital science, very good to illustrate, we see that when the batteries are connected, we call that end to end. Positive to negative, then the next negative to positive. This kind of connection is called a series connection. Now, when you have a series connection like this, let us take a look. Switch on. Let's see the brightness of the bulb. Are you seeing? Take note. I want you to note that brightness, and we will see another connection which is parallel. Look, have you seen the brightness there? Very good. Let's move to the next one. In the next one, now the batteries are connected side by side. We call that parallel. Parallel. Now, two things you should observe. What is the total voltage across the bulb? As you see there, up. The circuit is up. Total voltage. Do you see the total voltage? Let me point at it. Total voltage is 1.4. But for 4 batteries, 1.4. Let's go back. Let me go back to the previous one. Yes. Do you see the total voltage for 4 batteries? It is 5.6. What does that mean? That means when the batteries are connected end to end, you are adding the voltage. 1.4 plus 1.4 plus 1.4 plus 1.4 gives us 5.6. End to end. The light is very bright. Can I have the light again? Very bright. Now let's go to the next one. Side by side. That is called parallel connection. Now side by side, parallel connection, we see that the voltage is 1.4 as if it is only one battery. As if it is only one battery. Side by side. Let me point. One battery. Now look at the current though. The current is 5.6. Now the current has also increased. Now let's switch. If we switch on, do you see the brightness? Is it the same as the one in the earlier one? No. The earlier one is brighter. Now this experiment explains to us very important concepts that when you are loading, when you are connecting loads in your house, you must be very careful how the sockets are connected and how the switches for your lights are connected. I'd like to pose a question. You are seated there listening. How do you think the sockets are connected? You have a TV, you've got a fridge, you have a cooker, all of them are tapping power. How much power, how much voltage does each one take? Digital science has got the answer for us. That when you are connecting appliances in a house, particularly sockets, all the sockets must have the same voltage. Are we together? All the sockets should have the same voltage. Meaning there is a parallel connection somewhere. Same voltage. All these must be, that means all our sockets, the connection there in our mind must be, that is called a ring connection, but they must be connected in parallel so that the same voltage is taken. Now, if it's the same voltage, what does it mean to the current? If we look at our series and parallel connection, what does it mean? Same voltage, it means the current will be different, isn't it? Different current, same voltage. So let's look at this in digital science. I'm going to take you all the way to number 9 out of 35. Yes, number 9 out of 35 will give me that illustration. Do we see? Those are the appliances in your home. You have a toaster there in your home. You have a TV screen there in your home. So those sockets, they are all in parallel. That all the appliances. I want you to read with me. Let's read that statement. Very short. We read it together. 1, 2, 3, we go. Yeah. All appliances in our house are connected in parallel. That's the concept we have been reading. What's that? The reason? So that each one of them will have 220 to 240 volts across each and every appliance. That's very important physics concept, and it's applied here. All of them are connected in parallel. So, should you connect them in series? What will happen? I want you to pause and think. What do you think will happen if it is in series? If we look at our earlier animation, do we see what happens? The voltage will add. From 1.4, we add 1.4 plus 1.4. So imagine now you have 240 and 240 and 240. 4 times we are at 1,000. What will happen to the appliance? Boom! It will blow. Are we together? Do you feel me? Yes. So that is what we need to understand in this concept of parallel and series connection. I have just shown you, and you, all these appliances, you have them, the toaster in your kitchen, the cooker in your kitchen, the TV, the fridges, all of these must have the same voltage. That is the message I would like us to get today, that when the house is being wired, the sockets all have got the same voltage, meaning in our mind we should remember that this connection is called a parallel connection. The lights must have the same current passing through them. The lights, the bulbs in the house, same current passing through them. What kind of connection is that? Same current. Same current. So the light somehow must have something to do with series, the same current passing through the lights, so that they don't get blown. If the current increases, they are likely to be blown. Now, very quickly, we need to be safe. Electricity is not easy. Electricity is very dangerous. We need to be safe. I'd like just to show you how do we deal with sockets and appliances. It is very dangerous. Your fridge is there at home. Be careful that when you're handling electrical appliances, your hands must not be wet. Don't touch the wires which are bare. Just like the next person, let us see in the next illustration and the next one. Let me show you the next. This man here, for example. In your house, be very careful. Things which are metallic should not touch metallic wires. You get electrocuted. And this, in digital science, brings out very, very clearly the dangers associated with touching electrical wires, which with your bare hands, and metal touching metal, because those are conductors. Now, as a recap, what have you taken home today? What have you written down? One, we have looked at EMF, what it is. How do you get EMF? Open circuit. When no load is on and you switch on. Two, we've looked at potential difference. That is called terminal PD. When the switch is on and there is load, what the voltage reads is what we call terminal PD. We have looked at internal resistance. Are we together? Do we know what internal resistance is? Internal resistance, opposition to flow of current through the terminals of a battery. We have looked at connection, very important, which is a practical application of current electricity, that in the house, the sockets must be wired in parallel so that the loads in your house are all the same. There's a lot that you are able to get from digital science and virtual lab from Cyber School Technology Solutions. There are quizzes in there. There are even more virtual lab experiments that you can perform. I showed you one that is to find internal resistance. There are more virtual lab experiments you can perform at your own time when you have access to this wonderful software. It is available for you at Cyber School Technology Solutions. If your parent can have access to it, if your school has access to it, definitely ask your parent to come and have it installed on your laptop for you to use for revision during the holidays.
Now, I hope you managed to learn a thing or two on this edition of Digital Science for You. Remember, Digital Science for You is the show, and Digital Science and Virtual Lab is the software. For all of you administrators at different schools, you can acquire this different software via Cyber Schools Technology Solutions, via UMA Showgrounds, in Lugogo. You can also follow us on Twitter and Facebook, that is at CSTSUG for both Twitter and Facebook. Until next time on Digital Science for You, myself, Nicholas Namatrubobi, who's been your host. Enjoy the rest of your evening.